So hello there. My name is Cesar Lopez. I am CEO of Datumcon. Today we're going to cover a little bit about AI and deep learning applied for real-time data-driven decisions and how specifically we use SUSE Rancher and Kubernetes Rancher in order to orchestrate large-scale GPU types of deployments. So thank you for being here. I hope this session is somewhat useful. So the first thing that we're going to want to cover today has to do with the challenge of orchestration of GPU workers at the massive scale. And by this, I mean Kubernetes systems that will have the capacity of processing not just one video feed, two video feeds, 10 video feeds, but in the scale of hundreds or even thousands of concurrent video feeds at the same time. And how specifically is it that we use GPUs and we orchestrate all this via a Kubernetes Rancher SUSE type of solution. From that, we're also going to discuss a little bit the challenges around GPU scheduling with Kubernetes, specifically as it relates to scheduling around GPU resources, which is a very kind of new area. For a while, Kubernetes has done a very good job in scheduling pods and deployments based on RAM, based on storage, based on CPU cycles needed, and so on and so forth. But the idea of orchestration based on GPU resources is a little bit, how would I say this? It's a little bit newer per se. And this is the type of challenge that a company like Datumcon and many other companies out there will face as it relates to GPU orchestration. So I want to discuss and cover that a little bit and just give you guys an idea of how we tend to work around particular challenges and so on. And then also, more specifically, we're going to try to cover some of the challenges around scaling computer vision systems to hundreds of concurrent cameras. And then applying the same ideas also around how we can do also massively through multiple nodes, pods, deployments. We also process digital twins, which require a lot of 3D rendering, and how we can distribute that through multiple nodes, also via a Rancher SUSE Kubernetes type of solution and so on. So first, I want to talk a little bit about myself, just really quickly here. I am co-founder of Datumcon, and what we do in Datumcon is we develop, we train, and we serve neural networks. And we also create software to enable AI-driven decisions and operations for public and private organizations on 3 continents. Our main source of operation is in the GCC area, but we also run customers in not just in Dubai and Abu Dhabi, but in KSA, in Kuwait, in the US. We have a couple of customers over in the Texas, Louisiana area, Singapore, and so on and so forth. And pretty much everything that we build, once it's ready to go to production, we usually orchestrate it via SUSE Rancher. Everything we do, everything we run and we deliver usually goes over in a container. And it's built in such a way in terms of microservices that that we need to be able to scale it up based on the amount of processing that is required for the particular moment, that time, and so on. And we're heavily reliant on SUSE Rancher for all our cluster management type of needs and so on. And there's 2 main products that we have in a portfolio. One of them is a system called Insight AI, which essentially delivers real-time computer vision analytics at massive scale for hundreds or thousands of concurrent video feeds for all types of challenges, including HEC compliance, PPE compliance, oil rig management, port management, and so on and so forth. And we're also, we just recently launched our second category of products, which is a system called Twinverse.ai, by which we build urban scale, extremely large scale digital twins of entire sections of cities. And I'll explain a little bit more what I mean by that and also how specifically we use Kubernetes in order to be able to resolve this particular business challenge. So what's the challenge that we're talking about here? Well, essentially, the biggest challenge is to be able to orchestrate GPU workers at a massive scale. So more specifically, the item here is that we need to be able to automatically deploy specific quantities of containers to a set of host machines. And in the particular case of GPU workers, we need to be mindful of the resources available at every single individual node and how we're going to orchestrate a particular container or deployment and how it's going to be distributed over X, Y, Z amount of nodes. And for us in particular, the scheduling cannot be only dependent on RAM resources and CPU resources, storage resources. As a matter of fact, our biggest bottleneck is essentially GPU resources. So of course, being able to understand which hosts are currently being underutilized and can be used to deploy to more containers, or also be able to understand which nodes are being overutilized, which means that that the existing containers might not have enough resources and so on, and being able to keep track on that on a scalable system that might any given time be processing just a couple of video feeds, or sometimes it might be processing much more, a much bigger amount of video feeds at the same time. So being able to update and roll back applications running on multiple containers in different physical locations is also quite critical for us. And then we have to think about how are we going to load balance the application, both the traffic, the immense amount of traffic that you have in a video stream, but also the work itself, meaning the newer network that is doing the interpretation of the video stream in real time as it gets managed. So for that, we need to be able to use a centralized user interface that we can manage that those container workloads. And of course, items like kube control and non-GUI type of applications, they can work fine, but then eventually you're going to reach a point that you have so many nodes and so many containers that need to be able to auto scale or downscale that for us, nothing really beats SUSE Rancher and being able to get a good feeling of how our clusters are behaving and where the containers are being assigned in any particular nodes. For us, really nothing beats the type of orchestration that we can manage and keep an eye on via SUSE Rancher. But I'll get into more of that detail in a bit. And then, of course, being able to define the networking for the containers, because there's going to be different containers depending on the type of job. So in some cases, we would use some type of in-memory cache system, something like Redis, that has to be distributed in a particular way. Then you have something that perhaps maybe is ingesting a video stream, and that also has to be it has to be able to have network connectivity to the rest of the items, including the containers that actually have the newer networks themselves being able to process and the rest of it. And then as this keeps growing and growing, then the biggest problem becomes in a system in production is to be able to ensure the security best practices across a large number of containers. So these are the essential challenges that you will have when you're using orchestration for scaling GPU type of work and so on. And what the orchestrator does for you is that it allows you to manage the full container lifecycle from beginning to end. And you're able to scale the containers and the underlying infrastructure very easily, as quickly as you need. So you can just scale up, scale down, and you can just manage that via a very convenient front end like the one that Rancher SUSE provides. And then, of course, once as you're deploying services, and these services can be quite heterogeneous, they can be quite different one to another. Then you need to be able to provide a system by which all the services are being discovered, and that you have a way to handle the entirety of the networking between all the containers at hand and so on. While at the same time, you need to be able to implement security controls in a very consistent way. And then on top of that, uh, uh, since eventually you can end up with a lot of workers, a lot of containers out there doing their thing, then you have to be able to centralize container health and be able to handle fault tolerance for some of these applications that are constantly receiving video streams. And these video streams need to be processed in real time, and you cannot afford the luxury of downtime. And this is effectively a very high bandwidth type of work and so on. And then as you get more and more traffic, both from visitors that are looking at these video streams, but also traffic coming from the video streams themselves, then you have to be able to load balance the traffic between all these containers. And the end idea, of course, is to be able to manage optimal resource utilizations of the container nodes themselves. So before I jump into the specific type of tools that we actually use in order to be able to orchestrate decisions, I just want to take a moment here to be able to show what's a typical work space scenario for us. So what you're seeing here is a combination of multiple workers processing one video stream. This video stream in particular has several detections at hand. So as you can see there, it's detecting face. So that's one neural network. Then it's doing some kind of interpretation of the face. So it knows I'm a male. That's another neural network, and that's another container in some cases, another pod, so to speak. And then it's trying to determine my age. It's trying to determine if I have a mask or not, and then it's trying to determine an emotion. And for instance, in terms of a mask, I don't have a mask available here, but it's just gonna go ahead and cover myself. So it would assume that I have a mask. Let's see if that works properly. Yeah, there you go, with mask. And then a series of emotion of it. And then on top of that, you have another particular neural network, which is processing the same video frames, but in this case, it's doing something that is called pose recognition, by which it's determining the location of my eyes, of my body, of my body position, of my movement, and so on and so forth. And then you would just have some kind of object detection on top, by which I can just add to it, let's say a glass, or I could just add any object I would like, a cell phone or whatever I would like, and then it will do the recognition at the same time. So this, what you're seeing here, requires several containers working at the same time per video stream. So you have a microservice container that is actually running the video ingestion. Then you might have another container that is taking those video ingestion and maybe is putting it in some way that the frames are available to everybody else to process. Perhaps something like Redis or some kind of a memory cache system. Then you have another container that maybe is doing the face recognition. Then you have another container that might be doing the pose detection. Then you might have another container that is doing the face analysis, and so on and so forth. And this happens per every single video stream that is coming in. So once you have not just one, but hundreds of video streams, then the amount of containers and work pods, and workloads, I should say, that are needed in order to achieve this keep scaling up and up. So you can end up in a situation where you have several hundreds containers doing multiple types of works on multiple videos. And of course, the bandwidth utilization on this would be quite high, and the resource allocation on this would be quite high. So let me just go back to the presentation now that I've covered this. Okay, cool. So, so what tools do we use here exactly? Well, of course, we need GPU metrics, and there's plenty of monitoring stacks. Thankfully, on that, there's everything. We in particular we would use the Nvidia DCGM, coupled with Prometheus and Grafana. There's a couple of open source projects out there in the community that actually work quite well in order to be able to understand memory requirements and GPU types and GPU cycles available for every single one of the GPUs. And of course, in the particular case of NVIDIA, it's essential to be able to understand and deploy something that is called the NVIDIA Container Toolkit, which features the NVIDIA Container Runtime that allows you to build, deploy, orchestrate, and monitor GPU accelerated Docker containers. And most importantly, it needs to replace on the workers. It needs to replace the standard container runtime for the NVIDIA container runtime or whatever, or the AMD container runtime, depending on the type of GPU that is being used. But it's essentially a drop-in replacement that actually works quite well. And then, because you can imagine the scale of the type of workloads that it's going to be needed here, then obviously we use SUSE Rancher and RKey obviously for deploying the cluster itself, and SUSE Rancher for the orchestration management. I should say though that K3 is actually our preferred choice when we're doing computer vision on the extreme edge. But when we're doing computer vision on a centralized place with powerful GPUs, nodes typically on a data center, and we're trying to keep the latency low, which actually can be achieved quite low, then we usually prefer RTE on that particular item. So the key here is scheduling, obviously, and the issue with scheduling on GPUs is that there are alternatives available via device plugins, and those device plugins allow you to enable pods to access in this case the functionality of a GPU. This is not set up by default. You actually need to install it, and you need to configure it on the worker nodes that are going to have access to GPU resources and so on. And then based on your vendor, if it's going to be AMD or Nvidia, then you choose to install the GPU drivers that are applicable to that particular GPU's at hand and so on. And then after you install that, then Kubernetes is going to expose either an nvidia.com/GPU or an AMD.com/GPU as a schedulable resources, just like you have scheduled memory, scheduled RAM, scheduled storage, CPU resources, whatever. You can actually just set it up, just like any resources. You can just put it on your deployment YAML, and would actually schedule the right worker inside your cluster that has access to the GPU. But there's a big limit here, which is hard problem for us. The fact that you cannot overcommit GPUs. So containers and pods are not able to share one GPU. So you cannot have a pod request a part of a GPU, a subsection of the GPU. Essentially, each container receives full access to the GPU or to the multiple GPUs. And in the case of the device plugin, it actually reserves that GPU to that particular pod. So once it's reserved, then the GPU is not available for anybody else. And you can end up in a situation where you're underutilizing the resources because the containers are not actually using the full memory of the GPU, are not actually using the full power of the GPU cycles, but now they have essentially exclusivity to that particular pod. And when you're looking up in particular at inference, you can have a situation where an inference neural network deployed on a container tends to use more RAM, GPU RAM, that actually GPU cycles. And the reason why is because the neural network has to be loaded on memory in order to be quick enough and efficient enough. So once it receives a particular new piece of data, it can process it very quick in a matter of microseconds. I mean, you can achieve on a decent GPU, you can easily achieve 1,000 or 2,000 frames per second if you're thinking about video. As long as you have the neural network preloaded on memory. If you're trying to load the neural network every single time that you're going to do an inference, then the cost and your latency is going to be way, way too high. So, and Nvidia has offered a potential solution to this via a technology called MIG, which is multi-instance GPUs, but you can actually separate. It's called virtual GPUs, but this is only available in the Nvidia Ampere architecture, meaning the A100s, the H100s, the more expensive, the newer GPUs. For some very powerful GPUs, including for instance, the V100, this technology is not available there. So a way that we manage this, and there's a lot of interest in the community on how exactly are we able to share resources of GPUs between pods, because again, most of the GPU cards nowadays, they have a pretty large amount of GPU memory available to them, which might fit multiple neural networks on one GPU. So you want to be able to optimize those resources and so on. So again, there's a lot of interest in this community and the community on this. And there's one particular project that we feel is kind of like the most promising around it, which is the link that you're seeing on your screen, the GPU schedule extender, by which you can actually divide a GPU by GPU memory, and it actually makes it available to assign a percentage of a GPU. And it works quite well. We use it in production. The project itself is very in experimental phase, but we use it in production, and we've found very little issues, and it works quite well. So if you have the type of problem of how to share GPU resources, and maybe you realize that the standard device maybe you realize that the standard device plugin in Kubernetes of Nvidia or AMD is not doing it for you, and maybe you don't have access to multi-instance GPU MIG. Then this is actually a good alternative. You can assign a percentage of GPU RAM to a particular pod or a particular deployment, and then that allows you to be able to share GPU resources without having to worry that maybe a rogue container is gonna create a situation by which the entirety of the GPU is dead because of some memory leak or so on. But please take a look. This hit us very hard. Take a look at this particular pull, number 172. If you're running Kubernetes 1, 2, 3 plus, please do review that. But again, this project is actually quite cool. There's plenty of contributors of this project. It's growing every day. It's quite interesting. And hopefully one of the larger corporations, maybe even SUSE, might pick it up and help pro people like us that are trying to figure out how to share GPU resources in a more efficient way. But a couple things to keep in mind when you're scheduling GPU resources and you're writing your scheduler rules and so on. Well, keep in mind that you usually you need to preload the entirety of the model in GPU RAM. And this is not just in computer vision. This is essentially in any really quick inference type of situations. You need to be able to preload the entirety model, and so the RAM of the GPU is going to be constant. The use of RAM of the GPU is going to be constant per neural network. Once it's loaded, it just takes whatever GPU it's needed and it just keeps it there. Of course, there's certain servers that handle this to a degree and so on, but this is the general rule of thumb. But then the GPU cycles themselves are not typically used until some inference needs to happen. So if there's no inference pending, If you have multiple works that have the same copy of the neural networks running in multiple pods or multiple nodes even, maybe they're just talking to RabbitMQ or Redis, and they're just looking for jobs. And whenever they see a job, they actually use they actually have to do the inference, so they actually consume the GPU cycles. That's fine. You can have multiple workers on that. The only thing you have to worry about is the amount of GPU resources, and that ideally you want Kubernetes to be able to schedule that for you automatically, right? And not have a situation where you have one node that is over provisioned and the other node is underused. So that's just a typical problem that a lot of us in this a lot of us working on scaling up inference, we tend to find quite a bit and so on. So how is it exactly that we apply this? Well, essentially what we do here is that we create a situation that we may try to make sure that we're producing value from video streams. And that's what our product is about inside AI, which has the capacity of running videos in real time, producing a very large scale type of analytics, everything from face recognition to emotion recognition to license plate recognition to and HSE compliance, health and safety, equipment compliance, PPE compliance, ports management, airports management, and so on and so forth. We have over 30 different analytics for all kinds of businesses and problems and use case. And this is really a very strong product that's being used already in 3 continents and so on. And every single one of these deployments are usually just one pod, and it all fits in like Legos, and then you get the entirety of the system, which is inside AI. And again, we build one container per neural network, and that's what gets deployed into it and so on. So the scalability of it is to literally an unlimited amount of resources of it. And then this gets, this can be done either on edge via K3 or on cloud via RKE. And then you get a centralized processing of videos and the analytics on top of that. And thanks to SUSE Rancher, it's possible to set this up in a single multiple data center. So we have deployments where we're have replicating clusters where we have physical nodes on our data center, coupled with AWS GPU nodes on somewhere else, and they're both sharing the workloads. They're independent clusters, but they're orchestrated by the same rancher, SUSE Rancher, that allows us to just easily jump from one place to another, even working in some cases in air gapped environments and so on. So with scheduling, this type of situation, you also have to look at scaling. And so scheduling and scaling are defined differently depending on the type of worker. And again, you don't want the pod to take over the entirety of a GPU, because that's going to be a waste of available resources. So it depends on what you're looking at. So how do you, first of all, how do you schedule it? Well, there's going to be certain amount of containers that are GPU bound. So they have to be scheduled depending on the GPU resources. And this includes backends that include neural networks. This includes, in many cases, the software that is reading the camera stream. You want that to be efficient. And so if your pod is based, let's say, in FFmpeg, you can actually build a version of FFmpeg that is GPU, that does the codecs and the video conversion on GPU, so you can keep your latency way down as much as you can. So that can actually be GPU bound. And the WebRTC streamers, which is to be able to serve that content to potentially hundreds or thousands of people. You want that to be as low latency as possible. So it's nice to have a GPU. And the neural network will scale depending on the base, depending on the number of incoming streams. The WebRTC streamer will scale depending on the number of outgoing streams. But there's another reference. You can also have a system also scale based on the amount of neural networks that are needed for a particular job, or based on concurrent users and so on. And you can definitely have some workers that are CPU bound. So you can have a cluster coexist with some GPU workers and some CPU bound pods, and then just Rancher SUSE would just allow you to do that very, very easily. You can get more information about Insight AI on the website shown here. One last thing before I'm actually short of time. So now we're working on this particular new project, which is called Twinverse AI, which is a digital twin system that scales to city scale. And that same thing, it requires a massive amount of 3D rendering that has to be orchestrated via multiple nodes. And for that, again, we are counting on Kubernetes and specifically on Rancher, SUSE Rancher, to be able to orchestrate this huge amount of work of being able to 3D simulate everything from cities to airports to Mecca or in to Dubai airport, to an entire port, to an oil gas rig, and so on. So we are running this massive amounts of 3D renders, also using Rancher. And here the rule set for this is very similar. You scale the renderer depending on the amount of renders that you have there. So it needs to be able to scale up and down. Simulation also has its own criteria to scale up and down, and scheduling has its own criterion on this. So when you're architecturing a system like this, what you need your DevOps team to be able to figure out is what is the rule set for scheduling and what is the rule set for scaling. And as much as possible, if we can get more and more data about the performance of our GPUs, the same way that we have currently data about RAM available and storage available and so on, we can keep a tab on that, and we can make sure that the scheduler is balancing this out properly. Then the easier it's going to be for all of us to build real-time systems that are able to deliver real-time inference of machine learning models and so on. You can get more information about what Twinverse.ai at the website twinverse.ai. I'm actually out of time. That's all I got for now. My email is caal@datumcon.com. Feel free to write me up for any questions or comments that you might have. Thanks a bunch. Enjoy the conference, the rest of the conference.